right, we will pick up from where we left off on Friday. Okay, on Friday, we finished up 2.1. If you weren't here, that video's on Canvas. Okay. Work through that. We didn't have a whole lot we had left in 2.1. We got it finished Friday. Okay. So in 2.2, we're still working with sets. Okay. So we've got this section and then 2.3. So we'll have two more sections dealing with sets, okay, before we switch topics. So in 2.2, we're going to talk about something called subsets. And then we're also going to start using these things you're probably familiar with. You might not know them by name, but you're probably familiar with them. Venn diagrams, they help us when we're working with sets quite often. Okay. So the big idea, we do have some terminology, but the big idea is we want to get a feel for using these Venn diagrams to help us think about sets. They're really common. You've probably seen them before. So you may know what a Venn diagram is just by the name. Okay. Yeah, it is a diagram. Yep. Okay, so all it is, they get the name Venn because it's a person's name. Okay. A British logician there that popularized using these things. So all we're talking about with a Venn diagram, and you've seen them before, is where we've got, one circle that represents this group and one circle that represents this group, and they might overlap. You've seen them in memes and things. You'll see them there too. Okay, and we just kind of represent the relationship of one set to another set with these. So, and we use circles, but they don't have to be circles. They can just be some type of shape. Okay. Usually it's circular, so maybe an oval. So the idea, lots of times you may not see the universal set drawn, but we take a rectangular shape and use it to represent the universal set where we're working. And then we've got these circles or ovals that represent the different sets. Okay. That's all there is to the idea. Okay. So let's look at one. Usually, we'll label our circles or ovals. Okay. So here, like this circle on the left, we would say that's set S. Okay. And then the elements or the members in set S are the letters K, A, and S. Okay. We're doing there. Okay. So we've got a few questions we want to answer using this Venn diagram. So part A says list the elements in these three sets using roster notation. Okay. So for set S, we said we had the elements K, A, and S in there. Okay, so if we wanted to list set S, we'd have S equals curly bracket, and then we just list out the elements. Okay. There's set S. Okay. Set T, we could do the same thing. We're just looking at a different oval. And it might be a little hard to read, especially if you're in the back. That's a lowercase t, and then a lowercase j, and then M and D. And then what about V? Got B, C, and P. Yep. Okay. That's a little bit of a review on the roster method there. Mm-hmm. Which one? I'm sorry. Which symbol? The one right next. Oh, this. Okay, yeah. So this little looks like an E symbol, which just means that the thing that comes before it is a member of the set that comes after it. So this is saying that our universe is the set of all x's, such that x is a member of the English alphabet. So our universe would just be all the letters in the English alphabet. Yeah, good question. A reminder on that. And you can usually tell what your universal set is from looking at what the actual sets look like. We usually don't get too tricky in here. Okay. All right, B, let's just look at it. So you have to look at the notation here. B says find this thing for S, T, and V. Do you remember what that notation is? Telling us to find the cardinal number, or the cardinal number just means how many elements we have in each set. Okay. So the thing that looks like absolute value is cardinal number. So here, cardinal number of set S. We've got 3 elements in there. Cardinal number of set T. We've got 4 in that one. And then the cardinal number of set V. We've got 3 in that one. Okay. Remember, that's just how many elements we have in each one. How many members. Okay. All right. C says find T tick mark. Remember what the tick mark is? It's the, you can remember the name or what we'll have to do, either one, okay. T tick mark is T complement. Yeah, complement was the term. And then what is that? That's all the elements that are what? So this one's just kind of like the opposite, right? So it's all the elements that are not in T. Yeah? All the ones that are not in T is T complement. Okay, so if we want T complement, let's see, I'll do it down here at the bottom. Okay. So we don't want these, and we want everything else. That's what T complement's telling us. We don't want the ones in T, but we want all the other ones. And it doesn't matter what order you write them in. I guess I'm going to do KAS, and then ECP. Are we missing any? I kind of did a dirty math teacher trick on you there. That's not quite right. What are we missing? I set you up so you won't make this mistake. We want, all right, let's think back to our definition. Okay. We want all the letters, in this case, all the members that are not in T. Are these all the ones that are not in T? No. Wow, they're the one. These are the ones that are in S and in V. But what about the rest of them in the universe? They're not listed.
The ones that all the other letters in the alphabet aren't there.
Yeah. So what we want, what we need for T complement is we know we don't want these. Don't want these 4. T complement ends up being aggravating to write down because we want the alphabet except these 4. Alphabet except these 4. So not quite that. Not quite that. What do we want instead? Okay, we got to have a big ugly set. Okay, so just keep in mind these are the ones that we don't want. Okay, and then we're listing out everything else. So we got A, B, C. Nope, not D because D is in T. E, F, G, H, I, not J, because J's in T, K, L, not M, because M's in T, N, O, P, Q, R, S, and I'm gonna have to go down to the next line, okay? Not T, then we need U, V, W, X, Y. So everything except the ones in T. Okay? You can't just look at the other sets, you gotta look at the universal set. You gotta look at the universal that one. And when it comes test time, I will try to give you ones that are much shorter, okay, so you don't have to write all that out. It's really easy to miss one, okay, when you have that many to write out, so I'll try to give you a smaller universe. You don't have to write out so much stuff. Okay. The alphabet's a good example to use because we should know it, but it's also a bad example because there's so many letters in there. So. Questions on that one? Okay. One more. This one we don't have to write anything down for. This one says, we got two questions. Is S equal to V? Okay. And then once we answer that, we need to know, is S squiggle V? What's that one mean? You remember? Equivalent. Is it equivalent? So, is S equal to V? Well, S has the letters KAS. V has the letters ECP. So are they equal? No, because remember, in order for two sets to be equal, they have to have the same members, right, same elements. So these two sets are not equal. And then the second question says, is S equivalent to V? What do you say on that one? It is, because they have the same number, right? They have the same cardinal number. So that was our definition for equivalent. If they have the same number of elements, number of members, then they are equivalent. So they're not equal because they don't have the exact same elements, but they are equivalent because they have the same number of elements. Okay. Any questions on that part? Okay. All right, let's look at another Venn diagram here. Through all this, sorry. Okay. All right, again, remember our textbook's a little bit old, so it's a little bit behind the times here. It says there's an increasing number of electric vehicles on the roads in the United States. The number of charging stations available for these cars varies from state to state. States with the most electric charging stations are California, Florida, Oregon, Texas, and Washington. Okay, and then got a few sets here we're thinking about. So our universal set U, we're thinking about all the electric charging stations in the United States. And then the other ones, once you see one of them, they're kind of self-explanatory. The set C is going to be all the electric charging stations in California. Florida is all the charging stations in Florida. F is all the charging stations in Florida. O is all the charging stations in Oregon. So we're naming them by the first letter of the state. T is all the charging stations in Texas. W is all the charging stations in Washington. And then we're going to look at a Venn diagram. And on this Venn diagram, there's so many elements. Instead of listing out each element, what they do is they give us the cardinal number for each set. So it tells us how many charging stations are in each one. Okay, so that's a little bit different. Okay. Gives us the cardinal number. Okay. And we've got a few questions to answer for this one. Okay. This one says, which state has the most electric charging stations? Which one's got the biggest cardinal number there? Remember, these are the top 5, so C, yeah, California, right? And I've got 5,415, and I'm sure that's more than that now, okay? Because our textbook's a little bit old. Yeah, we got 5,415 in California. Okay, biggest cardinal number. All right, B says which state has the second highest number of charging stations? So T for Texas. Okay. Now, one thing to be a little careful of, and you might not have even noticed, okay, but on a Venn diagram, the size of the circles or the size of the ovals don't necessarily match up with the size of the set. Okay, because here, if you look, T is a little bit smaller than F up here, but it actually has more elements. So you can't trust the size on the picture, okay, with a Venn diagram. Okay. Not to scale necessarily. All right. C says how many electric charging stations do the top 5 states have altogether? How can we figure that out? Well, okay, I like the idea, but the universal set's going to give us all the charging stations in all the states. That one is. So we just want to know how many are in the top 5, so we can add them up. Right? We could take our cardinal number and add it up for those 5. Let's see what we get. Nerd, I've got my calculator in my back pocket here. So. I got 10,298. I don't know if I made a typo or not. Let's see. All right. Oh no, it was me. You're right. 99. I made a typo. Okay, so 10,299. That's what I got there. I'm getting the same thing if you checked it. Just adding those up. And then that's a setup problem for the next one. Okay, the last one says how many charging stations are in the United States but not in one of the top 5 states. So now we want to look at that universal set number. What can we do with that? We don't have to divide here. We can just subtract, but what do we subtract? Yeah, that last number we just got. Right? So this number tells us how many are in the whole country. We just figured out how many were in the top 5 states together. So we can just take this number minus the number we got on the last one. So let's see, we've got 19,996. Minus our number from last time, 10,299. Yep, 9,697. So this one was 10,299. Almost. Texas. Questions on figuring that out? No? Not too bad. You just got to remember, kind of had a theme. You got to remember that with the Venn diagram, just because you've got some sets and have the elements that are in those, that doesn't mean that there's nothing else out here. Sometimes you don't have everything represented on the Venn diagram. Okay. All right, so next idea. That is thinking about something called a subset. Okay. So with a subset, we can say one set is a subset of another set if every element of our new set is also an element of the original set. So we could say we're going to make a set, and the set is all the people in this classroom. Okay. So that would be our first set. We'll call that set A. And then we could say we're going to make another set, and in that second set, it's people that are in this classroom that are left-handed. Have any left-handed people? Okay, so you 3 would be in set B. And the idea here is that set B, the left-handed people, would be a subset of set A because all the left-handed people in here are also people in the room. And our notation there is a little weird. So it's like a C, and with an underline on it that says B is a subset of A. One way you can kind of think about it is similar in a lot of ways to like less than or equal. But we don't have an idea of less than or equal with sets, so but it kind of looks like that's kind of what I think about. So it just means is a subset of. All right, so let's think about what a subset would look like on a Venn diagram. That's our next little goal here. So let's look at this one. So it says our universal set's going to be the set of students at State University. Set W is going to be the set of students at State University that are majoring in computer science with a minor in business. And then set Y is going to be the set of students at State University majoring in computer science. We want to draw a Venn diagram to represent these sets. Okay. So anytime we're going to draw one of these, the way you'll see it in the book, all these problems in the book, is you'll see a rectangle drawn for the universal set. And then we want to draw in set W and set Y. But we've got to think about their relationship. So let's look back here. Does it look like one of these sets will be a subset of the other? What do you think? W's all students at this school majoring in computer science with a minor in business. And then Y is all the students at this school majoring in computer science. Yeah, so you stop and think about it here. Okay, so if you think about it the other way around, Y is the set of all the computer science majors. And then W is a little more specific, right? It's computer science majors that have a minor in business. Okay? So you could be a computer science major and have some other minor. Right? So there's more people in Y than in W. But for sure, everybody in W is also in Y. Okay? So here we would say W is a subset of Y. Okay? And if we write that down with our weird little notation, and say that. Okay? Really looks more like this. W is a subset of Y. So then when we draw our Venn diagram, it's usually easier to start with the bigger set. So here Y would have more members we would expect, so it doesn't matter where you draw it on there. Okay, so I would say that's set Y. And then where's W going to be? Is W going to be over here? No. Why? Because W is a subset of Y. We've got people that are in W and in Y. So W's got to be in there. It's got to be inside of Y. So Y's all computer science majors. And then W is all the computer science majors that also have a minor in business or whatever it was. Okay. Does that make sense? So anytime we have a subset, it's got to be inside of our circle or oval for the bigger set. Okay. Questions on that one? Okay. And again, yours doesn't have to look exactly like this. And just as long as you've got a W oval inside of a Y oval, then you're good. And draw it however you want from there. Let's look at another one. Okay. I'll give you a shot to draw this one. Okay. This is our universal set, our rectangle. It's a set of x's such that x is a computer. So our universe is all computers. A, the set of x is such that x is an iPad, so A is the set of all iPads. Then B is the set of all x's such that x is a tablet computer, so all tablet computers go in set B. So for sure you ought to at least be able to get U on there, huh? Here's U. Here's all our computers. And then let's think about our relationship between A and B. So is an iPad, is that a tablet computer? It is. It's a little tablet thing without a keyboard. Right? So iPads are tablet computers. But can you think of tablet computers that are not iPads? Yeah, like you got the Android versions, and Windows have got some that do their own thing too. That are little tablets. So which one's going to be the subset here? A is going to be a subset of B. So sketch that down on your drawing. You should have something like, here's our tablet computers, and then we've got a subset of tablet computers for iPads. Something like that. Questions on that one? Everybody sleepy today? You seem kind of worn out already, even though it's just because it's Monday. Get the Mondays. I get it. All right, so those are subsets. We do have kind of a weird situation going with subsets because our definition says in order for a set to be a subset, every element in that set has to be contained in the bigger set. So we have a weird kind of fringe case. Okay? So I could say we're going to make a set A. That's all the people in this classroom. And then I could say we're going to make another set, set B. That's all the people in this classroom. Okay, so same set, different name. Would set B be a subset of set A? By our definition, it would be. Okay, it's weird, but everybody that's in set B would be in set A, so that would be a subset. So the weird situation we have is if we have two sets that are exactly the same, if they're equal, they're subsets of each other. That's a little weird. We don't always like that. We don't want that to be considered sometimes when we're talking about subsets. So what we do is we can give it another name if you're not just a subset, but you're also not equal. Okay? So for sure, one is smaller than the other. And that name that we give sets is called a proper subset. Okay? So if we don't want to include the possibility that the two sets are the same, we're going to leave that possibility out. That we get what we call a proper subset. So another way of saying that is that there's at least one element in set A that's not in set B. That's another way of saying they're not equal. And our notation is just a little bit different. we still have that C-shaped symbol, but we don't have the bar underneath. So it's kind of like we, instead of dealing with less than or equal, we're just dealing with less than. Kind of similar notation there. So we're just saying there's no bar here. That means a proper subset. Okay. So let's work with this idea a little bit. Okay. Let's look at a set and then think about the subsets that could be made. Okay, so here's a set X. It has the elements 1, 2, and 3. We're told to list all of the proper subsets of X. So since it says proper, what that tells us is that the set 1, 2, 3 is not going to be on the list. Okay. That would be a subset, but not a proper subset. So then we want to think about the other combinations we could make. So what could we do? What else would be subsets of X? Let me get you started. What about the set that just has 1 in it? That would be a subset, be a proper subset. Think of any other ones? We got several to list out, so you might as well help me. What do you think? We're just thinking, we're just trying to take part of the set, right, to get a subset, proper subset. What else could we do? Not real chatty today, huh? Maybe we could do 2, 4, 3. We could do the set with just 3 in it. Good. Okay. Think of any other ways we can make a subset? Proper subset? 1 and 2. Good. Thank you. 1 and 2 would be a subset. The other one? 2 and 3. Like that. 1 and 3. Okay. Anything else? We said 1, 2, 3 is not on the list because we just want proper subsets. There's actually one more we're missing, and it's a little weird. Okay, but once you know it's got to go on the list, it's not hard. Okay, it's just kind of weird to think of the first time. Babe, what do you think? No? Okay. All right, so let's think about it like this, see if I can give you a hint. Okay. Here we've got sets that have 2 elements in them. Okay. Here we've got sets that have 1 element in them. And we're missing 1. Well, the order doesn't matter, so we're okay there. We said we can't have the set that has 3 elements in it, right? Because that would be this, and that would not be a proper subset. But what else could we have? We could have 0 elements. I like that. Okay, good. Good answer. And what's our set with 0 elements? Do you remember? It's the empty set. It's the empty set. So that counts. I know that's weird. If it kind of bothers you, it's okay. Kind of bothers me when I think about it sometimes. But if we're thinking about the possible subsets, then it's technically on there because you could have the empty set. So with that said, the empty set is a subset of every set. So it's always going to be on the list, so just remember it. Okay. There's all of our proper subsets. Okay. So the next thing to kind of think about is if we're trying to list out proper subsets for a set, it could be kind of easy to miss one, to overlook one. So it's helpful to know how many we're to expect. And so how many do we have here? We had 3 that had 2 elements, 3 that had 1 element, and then the empty set. So we had 7. That's 7. And what would be nice is if we could figure out some kind of relationship between we started with a set that had 3 elements and we ended up with 7 proper subsets. That way we could figure out how many to look for. Well, we do have a relationship for that. I'm not gonna make you figure it out on your own. Okay? But we do have a relationship for that. We'll get there in a second. Let's see if we can pick up on it a little bit. Let's do one more. List our subsets. This one's a little bit more tedious because we're starting off with 4 elements in our set. We want to list them. I like to go ahead and put the empty set first so I don't forget. And then what? Yeah, we can start listing them out, and you'll get tired. I got my words. You'll get tired of doing curly brackets. Okay, by the time you handwrite this out. Okay, we have A by itself, B by itself, C by itself, and D by itself. My brackets are already getting pretty bad. And they'll get really messy by the time we get finished. And there's A, B, C, D. Those are the 1 element subsets. Now we need to do pairs. Yeah, so we got A, B. AC, that's a good way to do it. Do all the ones that start with A. And then AD. Yeah. And yeah, BC. Because we've already got A and B in there, so go to BC and then BD. CD. Okay. And then remember, order doesn't matter, so it's the same thing when you switch the order. You don't have to write it again. Then on this one, we got one more round. We got to go the ones with 3 elements in there. So, yeah, I can do like ABC. Yeah, and BCD. ABD. And then, so we're missing A. Let's see. Let's check it. This is what I'm. Yeah, so here we left out A. Here we left out D. Here we left out C. So now we got to do. ACD. Yeah, the last one you're at. ACD. A lot of listing. And the more elements you get, the more subsets you get really quickly. So, like if you have a set of 10 elements and it says list out all the proper subsets, that would be a long list. Okay, so we're not going to do very big ones. But how many do we have here? Okay, let's see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So what's our pattern? It's not super easy to pick up on doing proper subsets especially, but let's look at it. Okay. All right, so this says if our cardinal number is n, so we have n elements in a set, then the pattern's a little bit easier to pick up on if you're looking at just subsets. We're going to have 2 to the power n subsets. Since we were doing proper subsets, we have to leave one out. Right? When we're doing proper subsets, we have to leave out the possibility we get the same set again. right? So we have to subtract 1 from that. We get 2n minus 1 proper subsets. So on the first one, when we had a cardinal number of 3, so our cardinal number was 3, and to figure out how many proper subsets we were going to have, we would do 2 to the third power minus 1. Let me write that differently. 2 times 2 times 2 is 8. So we got 7 proper subsets. And then that last one we did, our cardinal number was 4. So we do 2 to the fourth power minus 1. 2 times 2 is 4, times 2 is 8, times 2 is 16. So that gave us the 15 proper subsets we ended up with. Okay. And the only difference between proper and improper, is what you can call them, is that for proper subsets we have to subtract 1 to take out that case where we get the set back itself. Okay, if you're just doing subsets, you don't have to subtract the 1. Difference there. Okay. So let's end this section with a calculation, okay, of subsets. Semi-interesting problem. Okay. Probably not too interesting, but a little bit interesting. More interesting than what we've been doing. Okay. All right. It says Dr. Williams is eating at China Buffet one afternoon and notices they have a sign up that says so many possibilities. You could spend a lifetime eating at China Buffet and never have the same meal twice. Okay, so that's a pretty strong claim there. Okay. And then it says he wonders how many different plates he could make from the 16 items on the buffet. Okay, so they got 16 choices on the buffet. And for each meal, he could have all of the things on the buffet or none of the things on the buffet. He would still be hungry then. I don't know why he would do that. Or just some of the things on the buffet. We want to figure out how many different plates he could make. So what we're doing is we're making subsets. We have this set that has 16 items, the buffet. We want to know how many subsets we could make. So here we're not worried about proper subsets because it says he could have all of the items on the buffet. So that would not be a proper subset, but we'll count that 1. So we're just not going to subtract 1 at the end on this one. Okay. So we do our calculation, we figure out our cardinal number and it gives it to us. Right? The cardinal number, how many different items are on the buffet here? We've got 16. So to figure out the number of possible subsets, we would do 2 to the 16th power. Okay. So if we do 2 to the 16th power, do 2 to the 16th power, should get 65,536 different subsets for different meals. Right, well, we don't have to subtract 1 here because if he eats everything, we're counting that, that's okay. Okay. So that's our answer to the question, but then also, if we're testing the claim, right, it said you could eat there every day for your whole life and not have the same meal. So if we go that he's eating there once a day, 365 days in a year, then how long would you have to go before you ate the same meal again? That's really almost 180 years. Okay, 65,536 divided by 365. So unless you're planning to live to 181, their claim seems like it's pretty legit. Okay, seems like it's pretty legit. So those are big numbers you might not think about. Anyway. Questions on that one? That's not a hard problem to calculate. It's just something that's a little bit more fun to think about than some of the other ones. Okay. No questions? Okay. If you didn't get on the sign-on sheet, make sure you get on there before you leave. I'll get it and bring it up to the front up here. Don't forget, if you haven't done it yet, the 1.1 assignment's due by midnight tonight. Okay? If you have any trouble, let me know. If you have any questions, let me know. I will see you Wednesday.
Hey, you did get the email about
Yep. You're good to go. Thank you. Yeah, sign-in sheets up front if you need it.